Just going to talk about lists and dictionaries. So here's one-dimensional lists, which are by far the most common thing. I use these for almost everything. These are your all-purpose data structure for solving most problems. All right, so that's a list. You use square brackets and just put items separated by commas. You notice it's not a sorted list. These numbers are out of order, but we're going to print that. Then you can refer to an element. You can sort it with this. Put dot sort, and that automatically sorts it in place. I expected it sort of logically to be B equals A dot sort, but that's not what it is. The sort the list you refer to. In my opinion, there's some considerable inconsistencies in Python. It reminds me a little bit of like Microsoft products that way. It's not as, anyway, but that's the way it is. And so now after the sort, it's going to look different. And then we can append a number to the end, and we can change the first number, and all those things should work. So let's see. And here, okay. All right, so here's the list. That's a list. Here's an individual element, happens to be an integer. It could be a string or something else or a tuple. You can put any kind of data in a list, including a list, by the way. After sorting it, there it is, sorted nicely in order. There were two 2's, so there are still two 2's. It's not resolved to unique values. It's just sorted. And here's the print of the list after adding a 99 to the end and changing the first number to 100. So all those things are that's why I say this is your all-purpose data structure. It has all the good properties. You can change the elements, you can rearrange the elements, you can add more to the end. So usually those are enough features to do whatever you need to do. Sometimes they aren't, but most of the time that's the simplest structure to get the job done. All right, two-dimensional lists. I use them, although a lot of people learn to avoid them in more advanced Python programming, and I'm beginning to get there slowly. It is a list of lists. All right, so here I make a list A, B, and C, and then I make a list containing those three lists. D is A, B, C, and so this creates a list of lists, and you can refer to elements, D01, that will take you to the 0th element here, which is A, and then the first element of A, which is 2. So D01 is 2, and they're all mutable. Now, one thing that just hurt me yesterday is the same thing. So after I have D here, then I can set E equals D, right? I've just talked about this before. And now if I try to make that different, and I say D00 equals 100, and print E to see if E has changed. This is something I was telling you about last time, which very, very much annoys me about Python. So E has 100 there. So when I made a copy of D in E, it's just a pointer to the same list. So I said, well, I know the answer to this. I'll just do copy. I was doing this yesterday. And now I still get hosed because a list of lists, when you do a copy, the sub-elements are still just copies of pointers to the same object, which is very, very annoying. Perhaps this is obvious to you people, but coming from a world of Fortran and COBOL, this is not obvious to me. So I found the solution to this is this. I'm not trying to run, I'm trying to get to the beginning and add a line there. The solution is to import copy, and then you can do deep copy. All right, this is one solution, which is the one I tried yesterday after the first few hours of being frustrated. It's copy, deep copy of D. I think this one actually is like that. All right. There we go, it runs, and now my E didn't change or my D changed. So this is a solution. However, the better solution, and the one I'm going to, is to not do things this way. Come up with a smarter way to use lists. The reason I make multi-dimensional lists so hard to use is because they are really pretty sloppy way to solve most problems. There are smarter techniques, and I'm getting there. Anyway, this is something that has frustrated me for years about Python, and I'm slowly getting over it, where you copy something and it doesn't really make a copy. This is a time and space waster, though. If you were smarter, you would avoid making copies like this, and that's why they make it hard. Anyway, all right, so then there's dictionaries, which we talked about in the lecture, and we should play with them a bit. These are pretty useful. They're not as useful as lists, but they're often nice. All right, so the dictionary has a key and a value. So 1 is apple, 2 is baker, and 3 is cat. So we'll print it out, and then we'll print out the first element, and then I'll reset the first element, and that works. You're allowed to, but you have to refer to it by the index. So here's a list. 1 stands for apple, 2 stands for baker, 3 stands for cat. The individual element is a string. Could be anything, but it is strings in this case, and I can change the first one to alligator, and it's okay. Notice you can't have a second element number 1. Like if I tried, by the way, I don't even know if there's an append, but anyway, the point is, this is an index, and the index has to be unique. Let's see if I can append something. A.append. Let's first start with something good like for dog. Let's see if it'll do that. Nope, there is no append. Or rather, I might, no, I don't, yep, okay. Anyway, I'm sure you can append to a list. But anyway, I wanted to try to make a duplicate element of a list. Let me just see if I can figure out how to append to a list. Probably in your book, but I'll just do this. This is what I always do. I hope you do too. I just Google how to figure out how to do things. List append method. Well, not a list, append to a dictionary. That's what I want to do. Dictionary append. If you want to add a new key, use dictionary of key equals value. Okay, so that's what I thought. So it's going to prevent me from having a collision. So if I wanted to add another element, I would just set a for equals alligator, and that will put it at the end. But there is no way to have another element for. There's no way to append to the end. That's probably why they don't give you an append, because you might append something with the same key. Anyway, that's one thing about dictionaries. So they're useful if you have one element that is unique. And now we can play searching a list. This is the thing I mentioned before, searching an unordered list. So I've got an unordered list of common passwords here, I think about 50 of them. And I'm going to search for things. So and you can guess, while the guess is not equal to quit, it will run the search and tell you how long it took. So there we go. I'll guess a password, and I'll say apple. And it did not find it, and that took 10 to the minus 5 seconds. Now let's pick something in there, like 1, 2, 3, 4, 5, 6, right at the start. Okay, it found that in 3 times 10 to the minus 6 seconds, much faster. And if I take I love you, that's at the end, that should be longer. Yep, almost as long as failing, in fact longer than failing, which is kind of funny, but there's always some random factors in how long things take for such short lists. All right, so I'm going to quit. So that's the first step, trying a few searches. And now the challenge is get a list of 1,000 passwords and search through them, and then get a list of 1,000,000 passwords and search through them. And you'll see if an unsorted list, it really gets slow to hunt through it, because there's nothing faster than trying all the elements one by one. If you sorted it first, you could then do a binary search, which you talked about in class. Now, a binary search is much, much smarter. If the list is ordered, you look at the element in the middle and see am I before or after it. Then you cut the remaining area in half and see am I before or after it, and that's only going to scale as log of n instead of n. So you'll find it's much, much faster. And I think I have some example times here. Here's looking through 1,000,000, and looking through 1,000,000 passwords for things is taking about 2 milliseconds. 1 or 2 milliseconds is how long it's taking to find one password out of a list of 1,000,000. But in a binary search, it's incredibly fast, 30 microseconds. And it doesn't matter, because it only has to do like 10 or 20 guesses to split that list. In fact, 2 to the 20 is 1,000,000. So it'll have to do 20 guesses to find something, and it'll be, if it does find it, it will terminate earlier and take less than 20 guesses. If it fails, it will still only take 20 guesses. So your list of 1,000,000 is like a linear list that's only 20 long. So it's immensely better. Now, I learned about Bloom filters a couple weeks ago from the Security Now podcast, which are very interesting, and I thought I might add them to the class, but I'm not sure it's worth it because I don't think anything's faster than a binary search. I don't even think Bloom filters are faster than a binary search. But anyway, I may add them. We'll see. Anyway, so let me check on the Twitch for comments. I'm used to binary being flipped. The first number is 1, the lowest instead of the highest. Yeah, you could do it either way. Yeah, I may be violating some standard. I don't know the standards, so but anyway, by the way, this got me promotion at my job. I had a job where we were mailing letters, and we had to mail 1,200 letters to every travel agent in California, and we printed them all out, and a whole team of people stuffed them, and then there was one missing. And the boss said, "Oh no, this is terrible. We'll never find the one that's missing." And this happened last month too, and I had to apologize to the client, and I really don't want to embarrass myself telling the client we lost one. And I was the new guy, and I said, I can find it. He said, what do you mean you can find it? I said, I can find it. It will take a couple hours is all it will take, because humans can naturally sort things into 5 piles. So I just took the computer and printed a list of how many there should be, like from A to E, F to J, K to X. And we had 5 categories of letters, and we just sorted them in 5 piles, and they'll all be right except one that's missing one. And then you split that into 5, and split that into 5, exactly this procedure. And in a few hours we found it. And he was so happy. He thought he'd never find it. I said, it's not that hard, you can do it. So anyway, it was valuable in real financial work. Anyway, and in the real world, not just in computers. All right, let me stop this recording.